video, we're going to talk about how to find the power dissipated in each resistor. In this example, we have two resistors in series. We can call them R1 and R2. Now, in order to calculate the power dissipated by each resistor, we could use any one of the three formulas. Power is equal to voltage times current. It's also equal to the square of the current flowing in a resistor times the resistance. And it's also equal to the square of the voltage across a resistor divided by the resistance. Now, the first thing we need to do is calculate the total resistance of the series circuit. In the series circuit, RT is just the sum of each resistor. So the total resistance is going to be R1 is 20. So it's going to be 20 plus 10, which is 30 ohms. Next, we need to calculate the current flowing in the circuit. And we can use Ohm's law. It's going to be the voltage of the battery divided by the total resistance. That's 60 volts divided by 30 ohms. So we have a current of 2 amps flowing in the circuit. Now, because there's only one path for the current to flow, the current flowing through R1 and R2 is the same, it's 2 amps. Now that we have the current, let's use this formula to calculate the power dissipated by each resistor. So let's start with the first resistor. It's going to be the current flowing through it squared times R1. So it's 2 squared times 20 ohms. 2 squared is 4 times 20, that's 80. So that's the power dissipated by the first resistor. To calculate the power dissipated by the second resistor, it's going to be the square of the current times R2. So it's 2 squared times 10. So that's 4 times 10. That means that the second resistor is dissipating 40 watts. So let's think about what that means. Power is the rate at which energy is delivered to a device or to something. A power of 1 watt means that 1 joule of energy is delivered each second. So in 10 seconds, 10 joules of energy is being delivered. So R2, this resistor, is converting 40 joules of electrical energy into heat every second. R1 is converting 80 joules of electrical energy into heat every second. So in 10 seconds, it converts 800 joules of electrical energy into thermal energy. So that's the basic idea behind power dissipation. Now let's calculate the power delivered by the battery. To do that, we're just going to multiply the voltage by the current because we don't know what the resistance of the battery is. So the voltage of the battery is 60, the current flowing from it is 2 amps. So 60 times 2 amps is 120. Notice that the power delivered by the battery is equal to the sum of the power dissipated by the two resistors. This is in line with the law of conservation of energy. The energy that the battery delivers to the circuit should equal what the elements in the circuit are consuming. So the two resistors are using up 120 watts, the battery is delivering 120 watts, and those two values should be the same. If not, something is wrong. Now let's try another example. This time we have two resistors connected in parallel. Calculate the power dissipated by each resistor and also the power delivered by the battery. Feel free to pause the video if you want to try this. So first, we need to calculate the current flowing through each resistor, because it's not the same. Whenever you have two resistors connected in parallel, the voltage across them is the same. So the voltage across R1 and R2 is the same as the voltage of the battery, it's 20 volts. Now we could use Ohm's law to calculate the current flowing through each resistor. So to calculate I1, it's going to be the voltage across it divided by R1. So it's 20 volts divided by 5 ohms, which is 4. So we have a current of 4 amps flowing through R1. Now to calculate I2, voltage divided by R2. So it's 20 volts divided by 10 ohms, which is 2 amps. So that's the current flowing through R2. The current that is leaving the battery is the sum of these two currents. So the battery is delivering 6 amps of current to the circuit. Now let's calculate the power dissipated by each resistor. So starting with the first one, it's going to be I squared, or I1 squared, times R1. This time I1 and R2 are different. I1 is 4, R1 is 5. 4 times 5 is 20, times another 4, that's 80. So that's how much power the first resistor is dissipating. For the second one, it's going to be I2 squared times R2. So that's 2 squared times 10 ohms. 2 squared is 4 times 10, so that's 40 watts. Now the power delivered by the battery is going to be the voltage times the current. The voltage of the battery is 20 volts. The current flowing from the battery is 6 amps. 20 times 6 is 120 watts. So once again, the power delivered by the battery is equal to the sum of the power dissipated by the resistors. Number 3. A 220 ohm resistor has a maximum power rating of 0.5 watts. What is the maximum voltage that should be applied to this resistor? Now when you buy a resistor, there's two things that you'll know, or two pieces of information that you'll be given. That is the value of the resistor, the resistance, and the maximum power that it can handle. So once you have that information, when you're designing a circuit, you can determine what is the maximum voltage that you can safely apply to the resistor, or the maximum current that should be flowing through this resistor. And this example problem will help us to do that. So all we know is that R is equal to 220 ohms, and P is 0.5 watts. So to calculate the voltage, we can use this formula. P is equal to V squared over R. Multiplying both sides by R will give us the voltage. So V squared is equal to the power times R. Taking the square root of both sides, we get V. So the maximum voltage that should be applied to this resistor is the square root of the maximum power rating times the resistance. So that's going to be the square root of 0.5 times 220. Half of 220 is 110, so we need to take the square root of 110. And the square root of 110 is 10.49 volts. And that's a rounded answer. So that's the maximum voltage that should be applied. If you're applying 12 volts to this resistor, it's going to overheat and you can damage your component. Now, let's move on to part B. Let's calculate the maximum current that should be flowing through this resistor. So we're going to use this formula. P is equal to I squared times R. So let's solve for I. In order to solve for I, we need to divide both sides by R. So we get that I squared is equal to P over R. Next, we need to take the square root of both sides. So the maximum current is going to be equal to the square root of the maximum power, divided by R. So we know P is 0.5, R is 220. 0.5 divided by 220, that's 0.00227. And if we take the square root of that, it's going to be 0.04767, which I'm going to round to 8. And this is in amps. Now, if we multiply that by 1,000, there's 1,000 milliamps per 1 amp of current. This is going to be 47. I take this back. This should be 0.04767, which rounds to 0.0477. So this is going to be 47.7 milliamps. So that is the maximum current that should be applied, or rather, that should be flowing through that resistor. So now you know how to design a circuit if you know the maximum power rating of a resistor and the value of the resistance. You now know how to determine the maximum voltage that should be applied to the resistor and the maximum current that should be flowing in that resistor. Let's move on to number 4. A 6-volt battery is in series with a forward bias silicon diode and a 100 ohm resistor. Calculate the power dissipated by the diode. Assume the voltage drop of the silicon diode is 0.6 volts. So this is R, we'll call this D1. So we have a 100 ohm resistor and a diode with a forward voltage drop of 0.6 volts. And we have a 6-volt battery. In order to calculate the power dissipated by the diode, we need to know the current flowing through it. So how can we calculate the current flowing in this circuit? What we need to do is determine the current flowing through the resistor. And we can do that if we can determine the voltage across the resistor. Now what you need to understand is this. The voltage drop of the diode and the voltage drop of the resistor must equal the voltage of the battery. So to calculate the voltage drop across the resistor, it's going to be the voltage of the battery minus the voltage drop of the diode. So it's going to be 5.4 volts. According to Kirchhoff's voltage law, the sum of the voltages around a closed loop must add to 0. So this is positive 6, this is going to be negative 0.6, and negative 5.4. These are negative because they consume energy from the circuit, so they have a voltage drop. This is a voltage rise because it delivers energy to the circuit. But the sum of the voltages must add to 0 in a closed loop. So that's the voltage across the resistor, it's 5.4 volts. So to calculate the current flowing through the resistor, it's going to be the voltage across it divided by the resistance, based on Ohm's law. So the voltage is 5.4 volts, the resistance is 100 ohms. 5.4 divided by 100 is 0.054 amps. So that is the amount of current that is flowing in the circuit. Now let's calculate the power dissipated by the silicon diode. So it's going to be the voltage across the diode times the current flowing through it. We know the voltage across it is 0.6 volts. The current flowing through it is the same as the current flowing through the resistor because these two elements are in series with each other. So it's going to be 0.6 times 0.054, and thus the power dissipated by the diode is 0.0324 watts. And if you multiply that by 1,000, you'll get 32.4 milliwatts. So that's the power dissipated by the diode, that's how you can calculate it. Number 5. A 9-volt battery is in series with a 680 ohm resistor and a green LED with a forward voltage drop of 2 volts. Calculate the power dissipated by the LED. The process for solving this problem is the same as number 4. The only difference is we have a light emitting diode as opposed to a regular silicon diode. Now we know the voltage drop of this diode is 2 volts. That means that the voltage drop of the resistor is 7, because these two have to add up to 9. So now we can calculate the current flowing in the circuit, which is going to be the voltage across the resistor divided by the resistance. So that's 7 volts divided by the 680 ohm resistor. So 7 divided by 680, that's equal to a current of 0.01029 amps. Now that we have the current, we can calculate the power dissipated by the LED. So power is voltage times current. There's a voltage of 2 volts across the LED, and a current of 0.01029 amps flowing through it. So the power dissipated is going to be 0.02058. If we round it, it's like 59. This is 588. Multiplying that by 1,000, we can say this is approximately 20.6 milliwatts. So that's the power dissipated by the green LED.